Good morning, Professor. Good morning, everyone. In this work, we'll be shown the application of cost theory in systems involving rubber fabric. Uh, in the title, I asked the following question. Does the flapping of butterfly wings in Brazil set off a hole in a car tire in Texas? Uh, The title of the work is a joke on the phrase made by Edward Lawrence, which is, in an exaggerated way, a definition of how chaotic problems are sensitive to small initial conditions. Chaos theory is a field of natural science and mathematics dedicated to describing dynamic systems characterized by nonlinearity and high complexity in an essentially deterministic way. Situations like pinballs and with a forecast are systems that can be solved through chaos theory. Card games, dice, etc. are purely random problems. But if chaos is essentially deterministic, why is the wafer forecast given in terms of percentage? Uh, According to Lawrence, in practice, it may be impossible to purge a real system of recurrent randomness and observe the consequences. But often we can guess what this would be by turning to theory. Now, how can we correlate electromechanical coupling with Farragher theory in rubbers? In our work, we monitor the electrostatic behavior of natural rubbers and silicon rubbers conditioned to stretch cycles at 1 and 2 Hz. In general, we observed that there is a high reproducibility of results under same initial conditions. We also observed that the electrostatic behaviors tend significantly from the rupture process, as shown in this inside and in this inside. We also observed that the electrostatic behavior also latex rubber shows apparent surface change, indicating well-localized mechanochemical reactions. Another behavior that can be observed is the location of the crack. While latex tends to rupture closer to the fixed plate, silicon rupture tends to be more central region, in central region. But what geometrically within phase space, the attractor can be a point or a set of points and orbit in which the system tends to evolve. In dynamic systems, each point represents a system state. For a better understand, this program I made show the solution of complex nonlinear differential equations which have a non-periodic behavior. This is the attractor of the system, and this is the dot plot of the attractor. With the dot plot, we observe some more filled regions which show closer or more attracted orbits. To better understand the attraction point, we have a single pendulum and a damped pendulum. We observe in attractors that while for the damped pendulum we have only one attractor point, and the undamped pendulum one has all the coincident orbits. There is all orbits overlap. Returning to presentation. In our work, we represent the studious system using mathematical methods of Attractor in order to observe if the behavior of the system tends to diverge at some point, becoming chaotic. In fact, this could be observed. We observed both here and here that the behavior maintains same pattern until the emergence of crack. In addition, we monitor the electrostatic behavior along the rubbers when gradually stretched. Natural rubber has higher magnitude potentials near the fixed plate and null at the center. Already, the silicone has higher magnitude potentials at both plates and has no null potential anywhere in every sample. About the important analysis, microscope of pristine and cracked surface were also performed, both in SEN and AFN. We observed important topological changes after crack. Another important analysis performed was the digital image correlation, DIC, where we observed through images the distribution of mechanical deformation on the stratified surface. The results corroborated the electrostatic potentials.
I have 2 minutes.
Results showing greater strand gradient where there is greater magnitude of potentials. Continuing the work, we are trying the use of machine learning for failure prediction, molecular dynamics, and density functional theory to analyze the ionic distribution and interaction on and with the surface. In addition, we will investigate the influence of other conditions such as initial length, temperature, humidity, etc. My thanks to everyone who contributed. Thanks, Professor. Thanks to everyone. And end.